We're going to talk about what's called the data storage. Part 1, we divide this one in multiple parts, okay? So if you're interested to read more from the textbook here, we have another different resources. The database system, this one going to be cover the chapter 2. You already have access one, it's going to be available in the Blackboard. Yeah, data storage. Or there's another resource if you're interested with chapter 10 for the 6th edition for this textbook, or chapter 13 if you use the 7th edition. By the way, if I suppose not say that, but copy the database concept and this title, searching in the internet, definitely gonna find the 6th and the 7th edition. So it's available there. You can use them. Anyway, so starting last lecture, or this class, we need to learn how to build software that manage database in general. Okay? Our system design goal here. We are going to start, build the software that manages the database. Okay? What's the goal that we try to achieve here? We want that to provide that's like an illusion to the user or the database application or anyone, the user that use our database, that we have enough memory in order to store the entire database in memory. Yeah. What do you mean by this illusion here? To give the user in a way that I'm going to hide, or every time if the user try to access the data from the disk, I'm trying to hide this complexity to the user. In other words, I'm trying to minimize the impact that every time the application tries to access the data from the disk. Okay, so I'm trying to find a set of techniques that allow me and find a way in order to keep the pages or the blocks that the user asks for in the main memory. This allows to manage the database that exceeds the amount of the memory available. Again, the data stored in the disk. Then you need to find a way in order to fetch the data to the main memory once the user asks for the data. And the reason behind this one, I'm trying to reduce the number of disk input output operations, because these kind of operations are expensive. So I'm trying to avoid the largest tasks and the performance degradation. So let me show you here with more details. So at the beginning, we're going to start from the scratch. We're going to talk about what is called, the database file here. So the database file, which is the file we're going to store on the disk, can be stored as a sequence of blocks of the data. So here we can say, let me write here the database file. It might be files or files, okay? So this one is going to be in the disk. Assume this this is in the hard disk. This part, okay? So the database file is going to be stored as a blocks. So I have maybe one set of blocks of the data, okay? I'm going to show you today, starting with today, how can you do that, okay? And the first block, we're going to have what is called, special, block that help me in order to find my way access to these blocks of the data here. So we call this one here the directory. Okay, so we call this one actually, directory, which is to help me navigate my way inside the file. So again, I have a file. The file is going to be, stored as a blocks of the data. Each block is going to be stored in the disk. So for example, this file 1, block 1, block 2, and etc. I need to find the data structure in order to find my way within this database file. Because if you store the blocks in the disk, and you're going to lose the track for the blocks. You need to find a way in order, for example, for every single file, I'm going to tell you, for example, what do you need? I need a block 1. This is a block 1. Where is the next block? There. Where is the third block? Over there, and etc. That's what we're going to do for the first coding assignment. You're going to create a file using C language, and inside the file, you need to find a way in order to store the data inside the file as blocks. Okay? This is the first one. Then, at the higher level, the next level, what do you have here? We have what is called, the buffer pool. Okay? Or the buffer pool is going to do what? Is the unit that's responsible in order to fetch the data back and forth from the disk to the main memory. So here, the buffer pool, the same thing here. We do have a limited space Of course, we cannot take the whole memory. It's going to be the buffer pool. So assume this is, we have this space that we have the buffer pool. All of them are empty at the beginning. Okay, so we start with a file. The file is going to be break it up into a number of blocks, and these blocks are going to be stored in the disk. Then we need to find a way inside the files that allow me to find my way, which block I need to retrieve. We're done from this part. This is what's going to happen with the disk. Then the higher level here, we do have what is called the buffer pool. Okay, and assume that we have a user here, or the request asks, for example, I need page, let's say whatever. Let's say assume that I need page number 1. Okay, so the page number 1, if I got any request from the higher level, the first thing the buffer pool is gonna check and make sure whether I have a copy from the block that resides in the memory or not. If it's not, I need to do fetch. The directory of the file. Yeah. So the directory is one I have a copy from the directory. It's gonna be here. Then within this directory, it's gonna tell me, for example, you want page 1. Page 1 is located, let's say, in disk, specific disk. Disk specific, cylinder number specific, track, and etc. And specific block number. So all this information is gonna be given here. So I can then after that get back and fetch which block I need. So the fetch block is gonna be available in the main memory. Then after that, I'm gonna apply where, let's say, the block number 1 is gonna be have, for example, this is the pointer for the block number 1, so you can start working with it. Okay. So again, this is the first coding assignment. Gonna find a way how to store your data as files as blocks in the disk. Then after that, we're gonna implement the second other assignment, or the second coding assignment. We're gonna call the buffer pool, which allow me in order to fetch the block that is not available in the memory from the disk to the main memory. Okay, back and forth. Okay, so what do you mean back and forth? Usually when you fetch blocks to the main memory, the block is gonna be written or updated. So yeah, maybe we're gonna make minor modification to the block, so we need to store the block back to the disk here. Okay, so after that, what we need to take a look here, we need to see what the contents of the block. How can we store, let's say, records inside the blocks? Because remember, we are working with a database. Yeah, mostly we're going to work with the relational database, and the relational database is a set of what? A set of what is called it's going to be tuples, yeah, records. So I need to find a way how can you store the record within the blocks, which is going to be, this is the third coding assignment. That's what you're going to do in the third coding assignment. Okay, within the record, you're going to see that how can we store the attributes inside the record itself. Because you're going to see, for example, you're going to deal with different types of attributes. Char, varchar, it might be integer, it might be date, times 10, etc. So we need to figure a way how can we store this data, which is going to be the third coding assignment. Okay. Then after that, in the top, we're going to see later. Now I need to speed up the access to these data. So we are going to build the index, and we call this index, in our case, is going to be +3. This is the fourth coding assignment. So the fourth coding assignment is going to, this data structure is going to help me in order to figure out or speed up the access to the data. Okay? So that's what we try to do. And this is, allow us in order to build the way how can we store the data in the disk? How can we fetch the data back and forth to the main memory? Then how can we store the data inside the blocks? And then after that, how can we build the index structure that allow me, to speed up the access to the data? Okay, that's what we try to cover mainly in this class. Of course, at the top of that, we're going to study different mechanisms. One of them, for example, how can we recover from the failure crash, and also how can we achieve concurrency control. We are going to just only, study the theoretical part of these components, but we are not going to have time in order to implement or perform any implementation. Okay?
Yeah, it's clear.
Okay. So the question here, why we are going to waste our time and try to build, buffer pool, and also try to, for example, take the file and divide the file into blocks and to store the blocks in the disk. We need to do this one by ourselves. Why we cannot rely on the operating system in order to do this job here? Simple answer, the database knows better than, database system knows better than operating system. When you start, building our database management system here, when you start talk about the way that how can we create the blocks, how can we create, store the tuples inside the blocks, and also how can we arrange the block within the desk, the database management system is gonna be familiar, be aware with the content of the data. So it's gonna have a better idea. So the database management is gonna be better, a better position than to decide which block is gonna keep in the main memory, which one you need to get rid. How can we access the data? How can you anticipate, for example, this query is going to fetch or perform what you call sequential scan, and etc. Okay, and it's going to be much clearer with the time when you start talking about the buffer pool with more details. You're going to see sometimes you need to flush the dirty pages. What do you mean by the dirty pages? That means that the page of the blocks that resides in the main memory of the buffer pool, the content is changed. So we need to reflect the change to the disk. If you are going to rely on the operating system is going to wait until the block is going to be full. Then after that, it's going to perform, for example, the write operation to the disk. But sometimes we need to perform, for example, the eviction or the flush the dirty page right now to the disk. So in this case, because the buffer, the database management system, we're going to see that later when we talk about the logging techniques that allow us to know that to perform the recovery from the failures, from the cache failure, require from us to perform the flush date right now, not wait later. And also, we can perform what's called specialized prefetching. One of them, the double buffer fetch. If you have a double buffer, I know exactly how the data works, so I know exactly which block I need to fetch, because I am aware of the content of the data. I'm aware of how the data is going to work. Better buffer replacement policy, and also better performing the thread and process schedules. The most important thing you're going to think about this one, the operating system is not your friend. But I'm going to show you that there's a few places that we need to rely a little bit about the database, the operating system. So right now in the database storage, we do have two problems we're going to start looking at right now. The first one, we try to cover this one today. So the first one, how the database represent, database on files on disk. You have the database system you need to build, and your data is stored as a file. Yeah, and you need to take this file and store it in the disk. Of course, when you store this one in the disk, you have to represent this one in blocks. Okay? In more details, we need to take a look how to lay out the files in the disk as the blocks, and also how to lay out the data on disk in more details. And the second problem we need to think about to take a look at how the database managed its memory and move the data back and forth from the disk, which is the part that we're going to take care by the buffer pool. So today's agenda, I'm going to take a look at the first one here. How can we organize the database across this sequence of blocks with the file storage? Because the file storage is going to be blocks of data. Yeah. For example, maybe you have 5 or 6 blocks. Then how can we arrange these blocks? We're going to put this one next to each other. You're going to use a specific data structure in order to allow you, for example, in order to which order you are going to need to follow in order to store your data. And then after that, we're going to take a look how can we lay out the tuple inside the base. So we're going to take a look one at a time. Okay. So generally speaking, the database is going to do what? The system is going to store the database as one or more files on disk. Okay. It might be used a file hierarchy, or it might be used a single file. It depends what kind of database get you use. If you use a SQLite, this means one file database is going to store only in one file. The other database mainly is going to use like file hierarchy. That means there's the structure of the data. I'm not going to store all the database on one file. It's going to be a number of files, a set of files. And if you take a look to your favorite database system, you're going to see that how the file or database is going to be stored. So we don't have a single file, we have a number of files. Okay? And the most important thing, when I'm storing these data on the disk, the database, the operating system doesn't know anything about these files. The only thing that the operating system can see the data on the disk as a sequence of bytes. What does that mean? I don't know. If you ask the operating system to interpret, to explain what's going on inside this one, it's going to say, I don't know. There's only sequence of bytes. Okay? The only one that can understand, the content or can decipher what's going on inside these sequence of bytes is the database management system. And the reason why behind that, because the database management system know exactly what's the structure of this file, because who all create these files or these blocks of the data? The database management system. Okay. Storage manager is the software component that is responsible for what? For maintaining our database file on disk. Okay, within these files, and we will organize them as a collection of pages. So the simple thing here, the storage manager, this is the software or set of software that's responsible in order to work with the files, store the files as the blocks and organize them as a collection of pages. Okay, and in a collection of pages we need to keep track of the following. It's not like you just want to store the data, then good luck to find how can you find these pages. We need to find an organized way. We're going to show you different data structure we can follow that allow us to organize the page, the files as a page, and also allow us in order to track what the data, the writing onto pages, and the available space, and more different, extra information that help me in order to find my way or get some useful information about the blocks that's stored on the disk. So the first thing we take a look here, the database page here, okay? And the database management system is going to organize, the database across one or more files in the fixed blocks. And sometimes we call blocks of data, or sometimes called page. Okay? So the page, generally speaking, is what? Is a fixed size block of data. So if we take a look to the page, this is the page, okay, of block. It has a fixed size. Okay, it's not variable. Okay? It can contain a tuple, okay, metadata, index, log record. That means the content that you're gonna store to this block of this page is gonna be anything. It might be anything, okay? When I say it might be actual tuples, you know what do you mean by actual tuple? For example, you have a relation called student, and this student is gonna have the list of the scheme of this relation: student ID, name, and GPA, for example. So assume that we have 100 tuples of this data. This is what do you mean by the actual tuple. I need to find a way in order to store these tuple inside this block. The page or the blocks can contain the metadata itself. I can store the metadata in the block. I can store the index data. Later we're going to talk about the index. I'm going to show you how can we build the index, what data structure we're going to follow in order to build the index. So generally speaking, at the end it's going to be a file. Since it's a file, it's going to can be organized as a sequence of blocks. Yeah, it might be log record. It's going to be the content that be stored in this base. So we have many bases. Many data types, okay? So most systems don't mix page types. For example, most of the system don't prefer to have this fact. For example, I'm gonna fill this one with half of the page, for example, with tuples, okay? Then maybe after the sum of tuples that's gonna be, or data gonna belong to the index file, and other data gonna belong to the record. So you have a mixed data. Most database systems don't do that. So they have, for example, one page, for example, or a specific number of blocks that's only for the data, and they have another blocks or a specific number of blocks for the log entries or log record, and they have another separated block in order to deal with the index. Okay. Some databases require the page to be self-contained. What does that mean here? When you build your page or create your page, something like this, you need to keep all the information that's required and they need in order to interpret, the information about the page must be stored in the page itself. Okay, it's gonna be much clearer later when you start put data into the page. When you start with what the record of the page, and after that you're gonna see, oh, that makes sense. Okay, so how can we access this page? Each page is gonna have unique number, ID number. So we can use say it's gonna have like page number or page ID. It's like logical identifier for this page. Yeah, so the database management system is going to use this in order to do like interaction layers or mapping the page ID to the physical location. This the page ID, for example, equal 1. Okay, what does that mean here? That means it looks like we have a table, mapping table. It's going to say the page ID 1, and it's going to tell me what's the exact location of the page on the disk. And last lecture we talked about how can we store the data on the disk. So we all expect that the physical address must contain the disk ID, the cylinder number, and let's say the track number, and the block number or the offset inside the track, and etc. Okay. So in the higher level, remember when I showed it at the beginning of today's lecture, when I say the higher level, someone is going to ask, I want, for example, page, let's say, the query engine or the execution, they're going to say, I want to page number 1. Okay? So the page number 1 here, somehow the storage, so the storage manager would have what? You turn this one into the file in order to look up in this table in order to find the exact location in order to find the page that you're looking for. Okay? So the simple thing that the file is going to be stored as, let's say, a sequence of blocks or pages. The pages of the block is a fixed size, okay, that contains different many database or let's say page types. When you talk about the page type, it's going to be tuples, might be data tuples, might be metadata, index, or log records. And we emphasize that most systems don't mix, the database types. So when you have blocks, I'm going to keep information that belongs to the same relation or the same data type in the same place. So the reason behind why do we have a fixed size? The fixed size just in order to make our life easier, okay? Because if you have the database size different than, let's say, the operating system base or the block size. So now you need to do a lot of conversion between whether the size is larger, whether the size is smaller. If you try to use, variable size base, that's going to be not easy for you. You have to do, to do a lot of engineering overhead in order to make sure that to support these variable size, okay? And one example, for example, if you have a variable size and when you delete this one from, let's say, the file, it's not easy for you in order to fill this one with the new page because you are looking for the page that can fit in this space. So it was now we take a look to the data, a page in general, blocks. It looks like we have a different notation of the pages in the database management system. In the lower level, we have what is called, the hardware page, which is the one that we have in the desk level, okay? So different storage device has a different page size. Usually they have 4 kilobytes. This is the one, let's say, assume that that's what we covered last time. We talk about the disk, how the data can be stored in the disk. We assume that the smallest unit that we can retrieve the data was the sector, but sector is small. That's why we're gonna introduce what is called the page or the block. So the block, that's what I'm talking about. This is the hardware page, okay? So that's, as I said, this is a higher level. We have what's called the hardware page, and this is the size, okay? 4 kilobytes. Above from the hardware, we have what's called the operating system page. So the operating system is going to operate over the hardware, okay? And the size of the operating system page or block, usually 4 kilobytes. It depends by the operating system, yeah, in this case. Then after that, we do have what is called the database page here. So the database page was the one that, for example, I'm going to take a log from the storage device and put it in the memory. Let me do this one here, quick here. So you can see that we have in the lower level here, we have this operating system page, the hardware page. I'm going to write H the hardware page, for example. Then after that, in the top, we have the other page. We call this one the operating system page. And the operating system page would take whatever we have in the disk and put it in the buffer pool. That one is going to be like, that's why I said in the lower level, somehow we're going to need the help of operating system. The system call that involved actually the data, or fetch the data from the hard disk to the main memory is going to be performed through, the operating system. Then after that, the database management system is going to, take care of the control of the top. So again, with the database management system required, you need a page. It's going to say, I want to find the page. The page is not in my buffer pool. What we're going to do here, I need to issue input-output request to the operating system. Please, I want this page, that page. So the operating system, the only thing you do, take whatever the hardware page and put this one in the operating system page. Take whatever the hardware and put this one in the buffer pool. Okay? So here, the help. This part is going to be done by the help of the operating system. So the size of this one is 4 kilobytes, and the size of the operating system usually 4 kilobytes. And now we take a look at the top, it's going to be the database page. And now here is depends. It depends on what kind of, database that we have. I think SQLite and database and Oracle, the size is going to be up to 4 kilobytes. SQL Server, Postgres, they have 8 kilobytes. That means they're going to store more data. MySQL, the size of the database page is going to be 16 kilobytes. Okay? And yep.
I have a question.
Uh-huh.
So here hardware page is same as database page?
Same as what? The disk?
Database page. Like operating system is copying hardware page into disk, right?
The buffer. Yeah, I mean, you see, you have a database management system here. Database system, okay? When the database system tries to interact with the hardware, with the disk itself, okay? They cannot do this one directly. I have to go through the lower level, let's say, system call is gonna go through the operating system. Okay? So in order to try to fetch something or put something, it looks like you can say the database system page, it's gonna put whatever you want to put in the disk to the operating system page. And then operating system page is gonna store this data to the hard disk page. When you try to retrieve my data, the database management system, the one is going to be responsible, the one is going to say, I want this page, for example, number 5. So it's going to find exactly what's the location or position of page number 5, then instruct the operating system, say, please fetch that page from that disk to me.
Okay, so whatever operating system is fetching from hardware,
it's going to go to the database page.
Okay.
Because remember, that's one of the minor places that we need the help of the operating system.
Okay.
Yeah, because we cannot interact directly with the disk. Otherwise we have to write our own, let's say, system calls and API input output system call in order to allow us to directly access the disk. Okay.
Oh, yeah, got it.
So we do have one thing by the hardware page that's worth mentioning here that we call this one we mean here at this level that the device can guarantee what is called the fail-safe write. The fail-safe write, that means like a special property that it still has that the hardware, if you send any page to try to store this one to the disk, the hard disk is going to guarantee that the 4 kilobytes is going to be written as atomic as 1 unit. If you try to send something more than 3 or 4 kilobytes, I'm going to store the data in the 4 kilobyte size. Anything exceed this one, I'm going to divide this one into blocks of the data, and every time I'm going to guarantee that I'm going to store 4 kilobytes at a time.
I have one more question. So why is database page size is 1 to 16 KB?
Yeah, it depends on the database system. A database system doing database different stuff. For the SQLite, I guess it was 1 kilobyte. Then after that, they increased this one to the 4 kilobyte. And you can adjust. This is what is called, the default size. But we can modify this one. And many of database management systems allow you and increase the size. Yeah, but this is the default size. If you check the MySQL, you see the default size is 16 kilobytes. Postgres is 8 kilobytes. The Oracle, 4 kilobytes. I think that because the size is going to increase, add more data and details. It's going to store, for example, the page ID, and the page ID, I'm going to talk about this one later. Each database management system has its own format. The size, for example, I think some of them maybe you can say is 100 has, for example, just for example, it's not the accurate number. For example, 100 bytes, the other one maybe have 200 bytes. So increase the size of the page ID is going to be larger because it's going to contain more data.
Okay, so when it is MySQL, so like 16 KB, so it will be 4 hardware pages and then 4 OS page, like that?
It's it's for the hardware page is going to 4, operating system 4, but the database page is going to be 16.
No, I'm saying it will be 4 into 4 KB, so like that?
Yeah, so now I need to find a way. Now we have the data that's going to be sequences of blocks. How can you store, the blocks in the disk? Randomly? follow specific data structure. That's what we try to do. Remember, it looks like you are working in the warehouse, okay, and you get new stuff. I mean, next packages. What you need to do here, you have to find a way, structure way in order to organize your data. It's like label every package this belongs to whatever, which item, in order to organize this one, put it in the right place. Then later, when you try to retrieve the data, you know exactly how can we achieve or access or find out the package that you're looking for. The same thing here. The database management system needs the way in order to find the page on disk, given a page ID. And remember, from the higher level, someone will say, I need page 16. You need to find a way, how can we get the page 16 from the desk? Okay? So we do have a different, I mean, I like this statement that states that different database management systems do different stuff differently. Okay? Different database management system is going to manage pages in the file and the disk on different ways. The most common way to do that using the heap file organization, which I'm going to cover today. The other one, we can use sequential or sorted file organization. The other one uses, for example, the hash file, or the other one using tree files or tree structure. Okay, so the simple way to do that is the heap file. And the heap file that I don't care, it's like randomly just put this one anywhere, any place you can find. Remember, when you store the data on the disk, we are familiar with the structure of the disk. The disk has the cylinders, and you have tracks, and you have sectors, blocks. Yeah. When you want to store my data here for the heap file, put it in the first place, the random place. But of course, when you put this one in the random place, you need to figure out, keep tracking where you put it, because you need to retrieve it later. Okay. For the sequential, the one that's sorted file, keep the data sorted in the blocks. For example, it might be you store the data. I have data and the relation can be sorted based on the, let's say, the primary key. So I know I put the data in order for the block 1, then after that block 2, then after that block 3, then the rest is going to be block 4. When I'm storing my data, I need to try to store the block 1, then after that, next to this block, I'm going to store the block 2. And remember, we talk about the sequential. You try to put this one in the same track. If you cannot, put it in the same cylinders. Okay. The third one, we can use hash file in order to organize my data. And the fourth one, we're going to use the tree files. Later, when you talk about the indexing technique, we are going to cover the hashing file technique and the tree file. The tree structure that we use in order to build the index. And I'm going to show you, give you a simple idea. After we build the index, I'm going to say, instead we have index, we are going to have, let's say, blocks of the data in this case. So again, just we need to find organized way in order to find, or in order to store our data. Then after that, figure out a way in order to retrieve or find our page later. Okay. And remember here, in this level, this point, we don't know and need to know anything about the contents. It doesn't matter, what's the content of the data if you try to store the data in the heap file. When you say content of the data, that means I don't care about, whether the data is going to contain, let's say, index, or maybe it contains, let's say, tuples or data, or maybe it contains the log records and etc. Okay, so let's take a look at the database heap with the simple thing here. So the heap file again is an ordered collection of pages. So this means we're tuples that are stored in random order. This is the definition of the heap file. Yeah. So instead you have, in this case, we do have what? We have a collection of pages. That means it's going to be stored in random order. Whenever you have a space, just store this one. And of course, we need to make sure that in the data structure or the application that you use is allow you to create, to get, to write, to delete pages, and also allow you to support what is called, sequential access of the data, iterating over all the pages. And in most of the case, for example, assume the file contains your data or the information that, or relation called student. Then later you need to scan the entire relation. So in this case, in the heap file, once I store my data, I need to make sure that I find a way in order to allow me to iterate over all the blocks that belongs to this file in order to scan or retrieve the entire data. Okay, it needs, of course, some metadata, because you need to find a way in order to, or extra piece of information in order to show you or keep tracking whether the pages exist or not. This one thing. Yeah, whether you need to free space or not, because sometimes you need to store, let's say, tuple somewhere inside the data. Okay, so it looks like we need to let's give you quick here. So this is a file. Assume this is the hard disk, the whole thing. Okay, so I can put, for example, one block here, and then after that one block here. Then after that, maybe put this one here, put that one here. Okay, so those all the, let's say the blue one, that these blocks that belongs to file one, and maybe we have a blocks that belongs to another file, which is the red one somewhere. Yeah. Okay. If I organize my data randomly here, I need to find a way, another way, something. I need to have an extra piece of information. Let's have the yellow here. And this extra piece of information is going to tell me what? For example, okay, this file, you have, this is the page ID 1. This is the pointer where you can find page ID 1. This is the page ID 2, is somehow is there. This is page ID 3, and this is the page ID 4. Somehow, something like this. Not exactly, but something like this. So this one is gonna like, metadata that keep tracking which the pages exist or not. So let's see, for example, I ask you the higher level data set, I need page 15. Yeah? So what I'm gonna do here, assume that we don't have this structure. We didn't have this metadata, okay? So the simple solution that in order to retrieve the page, I need to retrieve all the blocks that belongs to this file. Then after that, check all of them. Are you page 15? No. 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 So we waste our time. We perform a lot of disk input auto version with nothing. But if we have this metadata, the extra piece of information or structure, so in this case, I need just to retrieve what is called the directory or page directory, okay? Then I retrieve this one in the main memory. Then I check, can you find page 15 here or not? So it looks like this one is gonna have extra piece of information, say those are the pages that exist, and this is the location or the where you can find them in the disk. And also it's gonna say for each page, maybe if I can do something like this page, this is the free space available in this page, this is the free space available in this page. Because later, when you try to insert one tuple, I can consult this page directory and tell me exactly where the pages that has enough space in order to fetch to the main memory. Then after that, insert the new record or tuple. Then after that, you need to write it back to the disk. You follow me, guys? So that's the way that we need to find the structured way in order to store our disk in the page in the disk. So there's a two-way in order to represent the data on the heap file. Okay, I just give you an idea of what we need to try to do here. The first way, which no one used, is based on linked list. And the second one, using what is called the page directory, was the most common or most database management system use this technique. But each of them might be, they have a very, different implementations. But from the high level, the structure is going to be the same. Okay? So here in this case, in the heap file, let me show you, start with the beginning here. So the heap file is something like this. I need to have, use the linked list. Remember, we are going to store our data somewhere randomly in the disk. Okay, but we need to build the data structure in order to allow me, how can you find my way? How can we figure out whether the base exists or not, whether there's a free space or not? Okay, so here, I'm gonna build a page, or let's say header, because I'm gonna implement this one using the linked list, and the linked list is gonna do what? It's gonna have a pointer to two different lists, linked lists. So we have a one pointer here, just has a pointer 1 here, and another pointer. So this page is gonna contain or compose of 2 pointers. Okay, each of them is gonna point to, let's say, a linked list. Clear? So this one linked list, and this pointer to another linked list. In this linked list, the first one is gonna point to the head of the free page list. That means it's gonna point to the list of the pages that has space, at least a space. It doesn't mean they are empty, but at least they have space left over. We can store some data inside this one. So assume this is gonna point to the head of the linked list, and this page is gonna point to the next page. Maybe we have, for example, 2 pages, for example, only they have free space, or they have some space. I know it's supposed my drawing must be accurate, but assume that the size is the same, okay? So inside this one is like, and when you build linked list, you know that you have 2 pointers. One pointer to the previous one, and one pointer to the next one. Yeah? That's what it is. So here we have one pointer to the previous one, and one pointer to the next one. If I don't have anything to point to, maybe it's gonna point to the end. There's nothing here. Okay. So this is one linked list that is going to have what, a free page list. That means the page that contains at least a space. They have a free space. Okay. Then after that, we have a pointer to the page of the list of the pages that contain that has these that there is no free space inside these pages. So assume that, for example, we have 3 of them. At the same structure, you need to go this one, but this is the subset of this linked list that contains all the pages that full, there is no more space, and this one's gonna be contains the list of the pages that have some space left over, so we can use in order to store our data. And again, you just need to find a way in order to organize by data. Okay, so back here to the slide. So that's what we have. We're going to have a header here, and the header has 2 pointers. One is gonna point to head, let's say, to the free page list, and this one is gonna be to another free, data page list, which contains the data is gonna be stored here. I mean, these pages are full. There's no more space. How can we implement this one? And we are going to implement this one with using linked list. Okay. In our case, we are gonna do the simple case. We are not gonna implement the linked list. We have a simple case. The first coding assignment. You have the file. You are going to store your data as a block in the file. You just to store like pointers inside the file using C language. Okay, so you don't need to go with a sophisticated process in order to build the linked list or the page direction. Clear the linked list. Again, the goal here, I'm going to store my blocks somewhere randomly, but I need to have built the data structure in order to allow me to navigate my way, to find my way, to see where I need check whether the pages exist or not, allow me to recover the page that I'm looking for. So for example, if you're looking for a page, okay, and you came here and decided and say, I want page, specific page, for example. I want to insert, let's say, a new tuple. So you're gonna go to the header. Every time you need to navigate your way, you have to fetch your header to the main memory. If you have enough space, then this header or this block must be stay in the main memory. Okay? Because the database management system knows that we're keeping access to the data file, so we need this blocking gonna be in the main memory. If we rely on the operating system, which is not the case, so the operating system maybe is gonna get rid of this block after we fetch the first time to the main memory, because the operating system maybe is gonna say, we don't use this one for a long time, or maybe we need the space to in the buffer pool in order to fetch another block, so it's gonna get this one vector block, we can get rid of it. So that causes us trouble because we need to perform another disk open out operation whenever we need to access or fetch data from the file. From the disk. But we are lucky because the database management system knows better about the structure, knows better what kind of operation you need to perform. So the database management system, the buffer pool implementation, is going to say, this header, keep this one, because this block we keeping access the data more frequently, so we don't need to waste our time every time to access the data, to fetch this block to the disk. Then after that, perform the search. Then after that, you have to get rid of this one, then fetch it again, and so the similar question here. I have a new tuple and I want to insert. So that means fetch this header to the main memory, and you can follow this pointer, tell you, for example, the pointer to the first block that contains space. Does this one tell me how much space? No. Based on this structure? No. That's why we said no one you use this one. Okay? So that means you have to fetch this block to the main memory. Then after that, check, do you have enough space to store this tuple? No. Fetch the next, and etc. Sometimes you're gonna fetch too many blocks until you figure out that you don't have enough space. Either you're gonna insert a new block, or maybe the last block in this linked list is the one that has a space. So that's why we said this is not good option. The other problem here, if I ask you, for example, I'm looking for a specific page. I will give you page number. Based on this structure, we cannot find out the page number easily. How can you find it? The only option for me, I need to scan the entire blocks here. If I didn't find it, I need to scan or fetch the entire blocks here, of the pages. If I found the page ID, then it's gonna be perfect. If I don't, that means I have to, so the worst case scenario, I need to scan the entire file in order to tell whether the pages exist or not. Then after that, you fetch. That's why I said this is not good option or good choice in order to build or structure our database. Okay? So the best solution, what, as I mentioned, the most database management system do is the following here. That's what you do. You call this one the page directory here. So now that we see, if you saw the first image when you talk about, I mean when you describe that, what you try to do here on the lower level on the file storage, we do have what is called the directory, because they need to find or navigate my way or data structure in order to help me how can I find my page after I store them into the disk. So the page directory is like simple thing here. So one special page, okay? So we're gonna have one page, and this page looks like something like this, and we'll call this one directory. And this page is gonna contain what? It's going to special page that tracks the location of the page database and the database files. Okay, the directory also stores, for example, the records. The number of free slots per page, and also give me, for example, more details. You can tell me whether the page exists or not. So in this case, it looks like here it's gonna tell me, for example, more details about the page. So what's gonna happen? It looks like we have more data here, number of free space, okay, and the location for this page. Okay. And another one for the next one, I have the same data, so it's gonna be give me some metadata where the data gonna be of the page this page, for example, located or stored, and also can give me, for example, the number of free slots in the page, and etc. So of course you have a page ID here. So here the page directory, if you try to look for specific pages exist or not, you need to fetch the page directory to the main memory, then you can scan. If you didn't find the page ID here, then done, the page does not exist. So you didn't need to waste your time to scan the entire pages of the disk. The second thing, for example, the same thing if you try to, for example, insert a new tuple in the database. So the simple thing you try to do here is see what? I need to find the blocks that have enough space, yes? So here just please take a look to the page directory. I can tell, for example, which page that have enough free space in order to store this tuple by just looking for the directory. Once you decide which one you need just to fetch this one to the main memory, then after that you insert the tuple. That's why it is much better than compared to the linked list. Clear, guys?
Yes.
Okay. So it looks like you are the only one who answered my questions. How about the rest? You still alive, guys?
Yeah, we're here.
Oh, thank you. Great. So after we're done from the file storage, we have the data, the file, we divide the file into blocks, then you find a way or organized way in order to store our block in the disk. Now we need to take a look to the page layout in more details here. What do you mean here? What the content, the structure of the page looks like from the side? Because I'm keeping talking about the page is going to be like a block. What's inside the block? Not yet. Now we need to take a look how the page looks like from the inside. Okay? So every page, generally speaking, is going to contain what's called header, which is the one important thing. Inside the page, there is a header. This header is going to, generally speaking, going to contain the metadata about the page content. It's going to help me more and store more details about the page itself. The first one is going to be what's the page size, the checksum, for example, the database management system used in order to version that used in order to create this database or this block. You know that you have different, your favorite database system that you work with, it has different, versions. So we need to make sure that to store what's the version used in order to create this page. Transaction visibility, for example, you know that you need to make sure that who transaction can be able to access this page and who cannot, and also conversion information. If you use any conversion technique in order to convert the content of the data, you have to tell me, I'll put this piece of information here in the header because you are going to use this information in order to deconvert the data. Okay, so at the beginning it's going to be half a block, empty page, and at the top it's going to be we have what is called the header. That header that contains metadata about the page content. Okay, some database or some system require the page to be self-contained, like Oracle. So in this case, what I need to do, I need to store more information, or you can say all the information that you need in order to understand the structure of the tuple that's stored in the data, in the page itself. So for any page storage architecture, we now need to understand how organized the data stored inside the page. That's one thing. Okay. And just for simplicity, we are going to take a look only one data types. We're going to assume that we are going to store the tuples, okay, of the relation in this table. Okay, so we do have different way in order to lay out, the data in the page. The first one, tuple oriented, and the second one, log structured. Okay, that's based on the storing in the page. Let's take a look at both of them and see what's the difference and when we're gonna use both of them. So the simple thing here, this is the tuple storage. That means I'm gonna show you a simple way how to store the data in the disk. Okay, when you say star man, idea, that means this is dumb idea. Don't use it. It's not gonna work. So the simple thing I'm gonna say, I'm gonna have only simple piece of information in the header, which could count, the number of tuples that's stored inside this page. Okay. So every time you try to insert a new page, I need to increase this one by one. Okay. So assume that we have 3 pages and insert the tuples. The first, the second, and the third tuple can be stored inside this page. Okay. Now we have a 3 tuples inside this data. What's the contents of the tuple? I don't know yet. Yeah. We assume that we have a fixed length tuple. That means each of them is gonna have the same exact size. For example, 100 bytes each, just for example. Okay, so in this case, the first, the second, and the third. Okay, so if we take a look here, what do you have, whether we have any problems here or not in this case. So what happens, for example, if you delete a tuple here? The simple thing we're gonna do here, I need to scan from the beginning until find this tuple, then delete it. Yeah, and after that you need to decrease the number of tuple by 1 here. So what if we have variable length attributes? What do you mean the variable length attributes? Before I go this one, what if you try to append a new tuple here? So you have 2 options. Either scan from the top until you find the first space, then after that you store this tuple, or maybe you need to add an extra piece of information to tell you the offset of the size of the one tuple, or the offset to the free space within this page in order to store your data. So you have many options here. The problem here, if we work with a variable length attributes, now we have a problem here. Because the variable length, for example, if you delete one, or you try to find, the right place or enough space inside the page, is not easy idea here. It's not easy job. That means we need to insert, to add more metadata in order to figure out how can we define, the free space, and also how can we navigate my way, how can we jump to that specific tuple. Because if the data fixed length, I need just to keep tracking of the size of each tuple here, and for me it's easy to jump. For example, I need tuple number 3 or the third tuple, so I need to count 100 jump. The first 100 gonna be the first tuple, the second 100 gonna be the second tuples, and etc. If you change the order, I need to figure out, it's not easy for me to find the exact tuple because I didn't have anything that added here the header in order to help me in order to answer the query. So that's why this is a bad idea. Why I'm not gonna cover no one use this one. So the second one was the most database system doing. We call this one the slotted pages. So you see that I'm adding more details. So this one can handle fixed or variable length tuple data. Okay, so the same structure. We have a page, and this page is gonna have a header, and inside the header is gonna have some metadata. Maybe can keep, for example, the number of user slots, how many slots use it, or the offset for the starting location for the last slot used. Then we do have data is gonna be divided, or the block is gonna be divided 2 parts. The first part of the top gonna have what's called the slotted pages. It looks like an array. Okay, and the array is going to have a pointer to the slot, to the specific tuple inside the data. Okay, and the slot array is going to keep tracking with the location for the start of each tuple. So for example, if I'm going, let me give you an example quick here. Assume our page is empty. Okay, nothing here, and we do have what you call here, this is a block. Then after, the header, and this here, for example, the slotted array. At the beginning, I have nothing. Okay, and this is the header. When you insert a new tuple, for example, I insert the tuple number 1 here. What I need to have, keep tracking and an offset, add an offset to what? It's going to add an offset to the beginning of each slot. If you want a page number 1, this is, the beginning. You have to jump to this place, then start reading until you finish. Of course, at the beginning, you're gonna see later for each block or a page, tuple, we're gonna add a header which is gonna tell me exactly what's the size of each tuple. Okay, so pointer to the beginning. If you insert a new one, for example, I insert 2 here, another tuple. So that means I need to add another slot here, and this is going to be pointed to the beginning of this tuple, and etc. So the way that the data is going to be, grow here, for the slot, it's going to be from the beginning to the end. This is the way it's going to go. Keep doing this one from the beginning to the end. And the way this, the tuple is going to be grow is going to be from the end to the beginning. At one specific point, they're going to meet in the somewhere in the middle. In this case, we are going to consider this page is going to be 4. So again, this is more organized way. So I have a header, I have a slot array. Every time I insert a new tuple, I need to have a pointer in the slot array point to the beginning of this block. Tuple that I just inserted. So when you try to search here, looking for anyone, which slot you need, you know that the page ID, you need, the address is going to contain the page ID and the slot, the offset within this page. So you know, for example, you need the tuple number 2. The tuple number 2 is gonna be the address is gonna give based on the page ID plus the offset inside this page. So it's gonna tell you the offset 2. So I have to follow this one in order to fetch this page, this tuple. Okay. So this is more organized way and better way. So we learned that how can we divide the data, store our file as a sequence of blocks in the disk. Then after that, we figure out a way using, page directory in order to figure out how can we find our way within the blocks. How can we navigate our way to see whether the block exists or not? How can we retrieve the specific block? How can we tell whether the block has enough space or not free space or etc. Then after that, we start taking a look to the page itself. How the page looks like from one side. Okay. So the best way in order to do that, we figure out that using the slotted page is the best way in order to organize or lay out, see the structure, lay out the tuple inside, the page itself. The other way we call that log structured file organization, which is a different way to perform this one. In this case, the previous one, what I'm inserting the tuple itself. And when you mean the tuple itself, it looks like here, we're gonna see the next, a few slides. But right now you can imagine that it's gonna be similar to the student ID, name, and GPA and address, etc. Okay. Of course, I'm not gonna store like this, but I'm gonna show you the structure. That's what I'm trying to store here. After we transform this one to the general representation. Here, I'm not going to insert the tuple itself. I'm going to insert the, let's say, the delta of the modification about the tuple. For example, when you insert something in the tuple, I'm going to insert the command itself. I'm going to say the log record, I'm inserting the ID 1, for example, and the value was A. Then after that, you insert a new tuple. I'm not going to insert put the tuple itself. I'm going to just append the log record. So the content is going to be different. It's not the tuple itself, but the log records. When you say the log records, that means the set of activities that you perform over this table, or this relation, or this file. So, for example, what I'm gonna insert, for example, insert the store, the entire tuple, and or delete or update. This is a modification: delete, update, and etc. And you keep growing until you reach adding to the end of this page. So, in other words, here we store what? The record of the file, how the database was modified, and I'm interested only for the insert, update, and delete. Okay, then. When you try to retrieve the data or read the record, how can you do this one? You have to scan the page backwards in order to start reconstruct the data of the page. So in this case, it's easy to insert or append the data. And it's hard to read the data because when reading that costs you time because you have to read, backwards in order to reconstruct the tuple in order to produce the result that you're looking for. So again, first, fast writes and also potentially slow reads. And the reason behind this one, we need to reconstruct the page that, the record on top of that we want to, use or access to. So there's one way to do that, just to speed up the access. Instead to, for example, I'm looking for the tuple ID equal 1 or 2. In this case, I need to scan the entire page from the beginning and up to the end. But we can build this, say, hash table or index in the top of this page in order to tell me, for example, how can I find my data. For example, if you're looking for the data belongs to the record or the ID equal 2, just follow this one. It's gonna tell me exactly where you find all the record. The data that modified by the record ID equal 2. This is 3, by the way. Okay. There is another way to deal with the log structured file organization that you need to do what? Periodically compact, the log file. Try to rebuild this one. Sometimes since you are inserting, modifying, and updating tuple, so what I'm going to do here, I'm going to compact this operation, write another insert, another update to the data. Another insert actually. Yeah, it looks like I'm going to insert a new tuple after recording all the modification or updates that happened for this record. So here, if we have, for example, tuple and made an update to it. For example, I already insert tuple, then after that make minor modification or set of modification, maybe 5, 6. Assume that we have a number of modifications to this tuple. Instead, in order to read this one again, I need to reconstruct this one. That's required for me to read, for example, 5 or 6 tuples. Yeah, in order to reconstruct the original or the new or the most updated version of the tuple. So what I'm gonna do in this case, I'm gonna compact all these operations that gonna happen on modification, or insertion, or updating over this tuple, and put this one based on the one in new insert operation. The problem, this one, I'm going to rewrite the same data over and over again. But it's gonna help me in this case because it's gonna speed up the access to the data, but it's gonna cost me another write operations. This what happened in the Cassandra, on HP base and the liberal database. They work with the log structure file organization. They use this one in order to organize the data. But mostly for the most database, the relational database management system that they're gonna work with the slotted page. This is the best way how to organize the tuple inside the page. So yep.
I did not understand in the previous slide. What do you mean by ends up with right amplification?
So that means if you have modified the tuple here in the slotted page, the normal thing, I'm going to insert inside the entire tuple. Okay. Assume the tuple that contains, let's say, student ID, student name, and GPA. Okay? If you try to modify this tuple, what you need to do here, you have to fetch the entire block to the main memory, then you have to fetch this tuple, then modify the data, then after that you have to store the entire, page back to the disk. Yeah? That's normally doing. Clear?
Yeah. Yeah.
But this one here, since we are going to store, we are not going to store the tuple itself. We are going to store only the log entries or the log records. What do you mean the log entries? That means I'm going to only store, the action that is going to perform over the tuple here. So for example, I'm going to say insert student ID equal value, GPA equals specific value. Then after this, that's what's going to be stored, something like this, insert and something, okay? Then after that, if you modify this ID or GPA with different value, I'm going to say update the ID, and this is the new value and the old value, something like this, okay? So I'm not going to store the data itself. I'm going to store the action, or let's say the set of operations that are going to modify the data of the tuple itself. So in this case, I'm interested in insert, update, or delete.
Yeah.
Yeah? That's the difference between two different file organizations or structure.
That is correct. But there it was mentioned like on the, I think the issue with the compaction ends up with right amplification.
Exactly.
So the issue with that, what we explained.
What happened here, for example, and you try to read the file, what you need to read the data the page backwards in order to reconstruct the file that you're looking for. Or you need to scan, for example, someone said, I want the user ID, the data that corresponds to the specific user, yeah, or the student. So what we're going to do, expect from you to build a tuple that contains student ID, student name, GPA, and etc. Yeah? You didn't have this information in one place. In this case, you have this information in one tuple, one place here, if you find the exact tuple. But in this structure, you have to build this tuple for us. So what we're going to do in this case, instead to scan the entire place on the entire page in order to build the tuple, I'm going to say, for example, since I'm modifying a lot and perform many operation over a specific tuple, I'm going to do what? But the last, I would say, perform a new insert, or maybe you can, the simple thing, you can delete this tuple, then insert a new tuple with the modification or most recent data that you update this tuple. So now when you try to read this one, you didn't need to reconstruct the whole bunch about this tuple. You need just to read only one log that has the final data that's stored in this tuple.
Okay.
So now we've done the first one. Again, we have the data in the file, store that, store the data as the blocks into disk. Then after that, in the page layout, we take a look at how can we organize the page inside the disk itself. So we're gonna use the page directory, yeah, right? What I have, what I've used in the page layout, yeah.
What is the question?
What the data structure that you use here, the page layout here, in order to put, the tuple inside the page. We used the slotted page. Yeah. Anyway, yeah. So now again, I have the data gonna blocks. Arrange the blocks. Then after that, I arrange. The blocks itself uses specific data structures. They just show you the heap organization. So we're gonna use the page directory in order to figure out or find out which block or where the blocks is gonna be stored and how can we access them. Whether which one is gonna have a free space and etc. Then after that, we take a look in the page layout inside. So that means how can you put the tuples or organize the data within the page itself. And we adopt that the slotted page. This is the best way in order to organize our data inside the page itself. Now we need to take a look how the tuple looks like inside the tuple itself. Yeah. So the tuple is essentially, a sequence of bytes. This is the simple thing that we can think about. Yeah. And the job of the database management system in order to find a way in order to interpret or translate these bytes into attribute or meaningful data in order to work with. Because when you try to store everything going to be stored in this level, it must be as a sequence, it's 0 and 1s, okay? Of course, we need to add extra piece of information. The only one that understands or can figure out what the structure, what we stored here, what kind of data is the database management system. So the simple thing here about the tuple layout is going to be here. You need to add what's called the header, which contains the metadata about the data, about the tuple itself. And this header is going to contain some information in order to help me to understand the sequence of the bits or bytes that's stored inside this one. So at the beginning here, there's a simple thing here. So this is the header. Something looks like this. The tuple itself. And I'm going to reserve, let's say, space for the header. And this header for the tuple is going to do what? It's going to contain, the metadata about the tuple itself. So it's going to tell me, for example, the visibility info. For example, who's going to access this tuple, or who cannot access this tuple, or for example, no one can, who the transaction can perform such operation over this tuple, or who not, or not. Who's the one that create this tuple or modify that tuple, and etc. Okay, and sometimes it's gonna have, for example, bitmap to the null values. Sometimes if you have some attributes are null, it's gonna have a pointer to them. It's gonna tell me, for example, if you're looking for the first attribute, the second attribute, for example, the data is null, don't waste your time to achieve anything. Yeah. So we don't need to store, the metadata about the schema of the database here. Okay, because let me give you a naive solution here. What if I store the schema here? Do you know what the schema, the structure of each tuple here? The schema of the table is going to tell me the structure, describing me the structure of the table itself. So it's going to contain what? It's going to contain mostly two pieces of information. That's what I'm trusting right now. The attribute name and the domain of each attribute. So in this case, I don't need to store the schema here for every single tuple that belongs to the database, because it's going to be waste of the space. If you do this one for the example for the first tuple, then after that you're going to store the schema of the database, or the relation is going to be here. So it looks like I'm going to just store this information that's not going to be redundant, and it's going to consume space, which can be used in order to store the data better than to just store for the schema, duplicate the schema that which can be stored in another place or outside. So maybe you can store this one in another block that contains the schema in order to allow me to how to access the data or to interpret the data here. So again, tuple header, tuple layout is going to contain or has what it's called, the tuple header, which contains the metadata about the tuple. Okay? So now we have a header here, and the rest of the data is going to be what? The attribute data that is going to be stored here. So what I'm going to do here, what do you mean that I'm just considering focusing the tuple data? I'm not focusing, for example, I'm not going to consider here different data can be stored in the page itself. For example, the indexing and etc. So here the tuple data is the actual data for the attributes. And assume that when you create table that you are familiar that there's a create command, a SQL command, a statement in order to create a table. And here we have a list of attributes, and for each of them have like the associated with the data type. So in order to store this one, the attributes is going to be, generally speaking, going to be stored in the order that you create your table. For example, the first attribute is A. That means I'm going to store the attribute A, then B, then C, then D, and etc. Okay. Most database management systems don't allow that the tuple be exceed the size of the page. Yeah, and we're gonna see later a few slides how can we deal in this situation. For example, if you try to insert attribute C and the size of attribute C is larger than the size of the page, how can I handle this situation? We're gonna see whether we're gonna use overflow or maybe use external storage in order to deal with this situation. Right now, think about, the tuple of it, they have a tuple. The structure of the tuple is going to compose the two parts, header and the attribute data, and the attribute data is going to be stored as the same order that specify them when you create the table itself. So, I didn't show you, for example, how exactly I'm going to store integer value or double value. We're going to cover this one later. Okay? So, what if, for example, I have two tables are related? We're going to take a look to what is called the denormalized, tuple data. Okay? Sometimes that the database figure out that this, the query that you perform over database mainly extracts the data that belongs to tables. Yeah? So it looks like it's better if we join the relations together in order to expedite, the access to the data or speed up the query processing. Okay? You are familiar with normalization technique. When you talk about the database design and when you generate entity relationship model, then after that you go through the normalization. That means you need to define what the good, bad thing. Then after that you try to make it better. Or you define the good thing, then you try to realize if you have a bad thing in your design, you have to split the data. So normalization, generally speaking, try to do what? Try to split relations. Denormalization, that means try to rejoin them back. And the reason about this one here, just in order to explain the access to the data. Okay? So we can physically denormalize or rejoin the related tuples and store them together in the same page. So later, when you have a query that try to extract the data that belongs, get involved to join operation from both relations, I'm gonna just go to the block, and once you fetch one block, I'm gonna find all the tuples that I'm looking for, because the tuples that gonna belongs to two relations gonna be stored in the same block. It's better than if you have, for example, stored the table full information one block or separate block than the bar. So every time you're gonna try to fetch the data, you have to go to the block. Fetch one block from the full. Then after that, you have to fetch another block that contains the tuple that from the bar, which cost me another, extra disk input out operation. So here again, there's the simple case, which the one that I try to avoid here. I'm going to have, for example, separate block for the food relation, and I have a separate block for the bar relations. And I know here the bar relation is going to have a reference, foreign key, which is going to reference, to the primary key to the other relations. So it looks like it's going to be connected. Every time you try to access here, you have to fetch somehow you need to, to access the data that's stored in the other table. So here we have a header, the same structure here with the tuple inside the full block, and we have, for example, the attribute data, which A and B. Again, I didn't specify exactly how can store integer value. We're gonna cover this one later. Just now think about it. We're gonna need to store the attributes in the order that we create the table. Okay. Then this is the bar, and here the bar, for example, in our case, assume that we have one tuple, and here we have 3 tuples. Okay, just for simplest. So every time we try to access the data, you see that can undo this one in one relation or one table, one tuple. So what I'm gonna do here, I'm gonna have one tuple. At the beginning, we have a header. Then I need to store the value of A and B. And every time you see this value, if A and B, and every time A is gonna be referenced to the, this relation is going to be a reference to the full. That means I can store the corresponding data that's stored in the other table with the CA. So how many C's do you have? For example, you have a 3 value of C for the specific value of A. So in this case, I'm going to build one tuple, again, header, A, B, and I know A is going to fetch, rejoin the data from that belongs to the other block, in the other relation, in the same tuple. So in this case, I need just to repeat the value of C's 3 times based on the data that we have here. So just an example here. So this one data belongs to the full, this data belongs to the bar. So I'm going to rejoin the data, it looks like, and mix the tuple that is going to contain information that belongs to 2 different relations. And etc. Continue to do the rest. So this is the first entry. This is the second, and so it's, if you have more data, sometimes maybe you have more data that's going to be stored here. Okay. So using this data, if you try to, answer a query that involve data from fetch data from full and bar, this is going to be much easier for me. Because when you fetch this block, I'm going to find all the information that I'm looking for. So remember, queries that involve full and bar, attributes belongs to relations. Every time you fetch one block, you're going to find all the information that you're looking for. Yeah, of course, the size or the number of tuples is going to be less here, but at least it's going to reduce, hopefully that we achieve a less number of discomfort out operation. Again, the goal of us here, try to mitigate the effect, the access to the data, and also try to mitigate, or reduce the number of discomfort out operation you need to perform, because it's a bottleneck for the whole database management system performance. And the reason behind this one, hopefully it was clear last time when we started talking about the disk, how the data is going to be laid out the disk, and how to compute the access time. Every time you need to move the header back and forth, and cylinder is going to be rotate, platter is going to be rotate until we find, the right place and etc. Okay, this is gonna, this advantage using this structure is going to have what's called make the update more expensive. Why in this case? Because generally speaking, sometimes when you update, you need maybe the update only the value that or attribute belongs either to full or bar. In this case, every time to fetch one block, it's going to have less number of tuples. That's me required for me to do more number of disk input out operation. You compare this one if you have 2 separate blocks, and each block, or let's say you are going to store the data that belongs to one relation together, and the other separately than the relation bar. So in this case, when you try to access the data and fetch one block, hopefully this block is going to contain number of tuples, at least all the tuples has a header and only 2 attributes that belongs to the full. That means we maybe be allowed to have more or large number of disk, tuples can be stored in this box. Okay. The record ID, we do have what's called, as we have what is called, the tuple ID, we do have what is called, record ID. And the record ID here, it's like a database management system required a way in order to keep tracking of the tuple that's stored inside the database. The same way that it needs to keep tracking to the page, it needs to track, keep track to the record ID. In the record ID, we can use what is called unique record identifier, that can be associated for every single tuple, and this record is going to have what? It's going to have the page ID plus the offset inside this page. Yeah, and remember here, it looks like we have something like this here. So here, this is a page that we have. If we have, for example, I need the record ID for the tuple 2, it's going to have 2 things. It's going to have the page ID, which page the tuple is stored, and also what's the slot or offset inside this page in order to find my way here. For example, it's going to be number, for example, page tuple 2, so it's going to be the page 5, whatever, and it's going to slot, it's going to be 1 or 2. It's going to be 2. That means I need to the second slot in order to retrieve my data. Okay. Only use this one only for the internal representation. You cannot use this one in order to perform the query. So next lecture, I'm going to give you like tutorial. We'll try to go through like work with the postgres. I'm going to show you, for example, how can we identify the record ID that's stored using, in my data, and also we're going to show you and convince you that we cannot rely on this record ID in order to retrieve the data, because you're going to see later what I'm going to do. I'm going to create a table. Then after that, we're going to store the table in the disk. I'm going to show you what's the page ID, what's the record ID for every single tuple that we stored in the disk. Then after that, we're going to perform minor modification, delete, modify the data, and etc. And you're going to see the record ID going to be changed every time. Yeah, that's why we cannot rely on this record ID in order to retrieve the record. Based on the application. But for the internal representation, yes, because the database management system is going to keep tracking for the record ID. So let me now do like quick tutorial. Let me check first. I need to go test this one using the postgres. So it's going to be the same way if you try to use it with different database system. Okay. Okay. This is PG admin. I think we can see that. Give me a second. I need my data here. Okay. So what I'm going to do here, let's create small table or tiny table that contains this information. Okay. I'm lazy guy, copy paste. Okay. So assume that we have a table A that has the ID and name. So 2 attributes. Okay. And on this one, we create this table. So the table is existing. Now let's fill the table with data. Okay. And assume that I'm gonna fill this one with this information. So the ID is gonna be let's say Alice 100, Alice 200, Bob 300, Eve, and whatever. Okay. Now let's take a look at the information that's stored there. Just to make sure that we're on the same page and we understand what's going on. Okay. I just select all the information there, and this is the data gonna be stored here. Clear? So far so good. Now let's show you that the inner representation, how the database management system or the postgres identify or create, or let's say what the value can be stored in the CID, the record or tuple ID they use in the postgres. Okay. In order to perform that, I'm gonna use what is CTID, okay, which contains the record ID or the tuple ID. In order to perform that, we can use the following here. You can say TID, comma star, or the rest, whatever the relation A to star, maybe you can do that, and the rest of the A, okay, or star. Anyway, I'm interested here. So it's like a special attribute we can query, okay, in order to retrieve the data there. I don't know what I did. Okay. So here we see what? It's something new tuple or new column here that contains like a pair value. The first one, the 0, means that the data, I think, can I draw here? No, I can't. Anyway, the 0, that means this is the page 0, and 1, that means the first offset. Okay, this is the first page, this tuple is going to be stored here. That means all of them the same page, and each of them is going to has like the slot number inside this page. Clear? So someone said, okay, can I use CTID in order to, let's say, retrieve the data? Yes, for now. But remember, if you organize your data, everything can be lost. Okay, that might have a different value. Let's play around. What if I said I want to delete, let's say, specific tuple? Which tuple are you going to delete? Let's delete someone in the middle, okay? Here, 200. So I'm going to delete this data and see what's going to happen. I think I need to use a different one because easy. I'm lazy guy. Delete from A where the ID equal 200 and around here. Okay. Then let me give me the value, how the value looks like. So I want just to select all the data stored there. Oh, let me go back here. What's happened here? You see that the CTID 1, 3, The one that used to be 02, or the slot 0 or slot 2, which used to point to the tuple 2, it's not existing. Okay, the system don't organize anything. Still have the slot 1, slot 3. So slot 2 is like unused. Okay, so how about we need to insert a new value here. So I'm gonna insert this, say, new tuple, and this tuple is gonna have like 200. Okay, we delete 200 here. If you check here, I delete 200 here. So let's insert a new tuple, 200, and the value is asked. Even the same value doesn't matter. I run this one, insert this one. Now take a look, see the content here. Let me run again to see what's gonna happen. So let me ask you a question. Where do you expect the new tuple to be inserted? And under what slot? Just speaking, it's gonna insert this one at the end. Okay, let me see. But the bottom. The continue. Okay, remember, because you it looks like when you delete something, it's gonna be marked as a delete, but it's not gonna change. The place is gonna be there. When this one's gonna be completely deleted, when you do perform like reorganize your tables or your data. So now you see that if you keep adding, even if you do the same value, it's gonna be added to the next and the next and the next. Okay. So how about I'm gonna perform what's called, let's say, reorganize all the tables that we have. We do have like vacuum for, I guess, let me check here. That just do what? It's going to take a look at the old database, the table that we have in the database, reorganize the data. What does that mean, reorganize the data? Now it's going to take a look and say, oh, I used to have a slot is empty. No one is, for example, slot 2 is available. Now I need to shift from the bottom, it's going to be the one is used to slot 3, it's going to be the slot 2. The one in slot 4 is going to be slot 4, 3, and etc. So it's like reclaiming any space available there, rebuild every single index that we have, because now we need to refresh the record ID with the new value. Yeah, it depends on the data that you work with. I don't have a lot of data in this machine. I use this one just for teaching class. The other machine talks longer because it has more data. But this one is going to be faster. Hopefully it's going to be faster. Okay. When you run this one, it takes a few time, and now it's done. Okay. Now let's take a look again. I'll do that query again to see what happened here. If you run your query here, you see that 1, 2, 3. That's why I said this is the CTID. I'll just give you an idea how the data can be organized. If you have a large amount of data, you're gonna see this one maybe gonna be changed. You have seen many blocks that are gonna be stored there. It depends on the size of the block. It depends on the size of the tuples, etc. And again, we don't rely on the record ID in order to use, for example, perform a query, because it's gonna be changed. Okay, it's not, static. It's not like the primary key that we have the data as well. So right now, if we try to retrieve the data that have the CTID, for example, 01, you see that later when you, or 02, later maybe you're gonna have a different tuple. It's gonna be point to another tuple after you organize the data. Okay, hopefully that at least explain or show us what's going on in this part. Okay, so take a look at what we did so far. We took a look at the database itself. Our database is organized in the files. The files can be organized in the pages, and we find out the data structure in order to allow me in order to find, keep tracking to the pages within the disk, and also can retrieve and tell whether the pages exist or not. And we use the page directory in order to take care of this one. And also after that, we take a look, to store, the ways to store the pages, yeah. And we go through, slotted page was the best way in order to organize the page. Then after that, we take a look, how can we store the tuples itself? And I guess now we are ready to take a look to how can we store, the attributes within the tuple itself. It was the internal representation. For example, what you have in the tuple, we have a student ID, student name, etc. Each attribute is going to have its own, let's say, data types. So we need to find a way in order to how can we deal with different data types, how can we store them in the disk, and etc. Okay, so next I'm going to take a look at what's called the value representations, and we continue talking about the storage model in more details. So we're going to continue our discussion about the database storage. Okay, so what we did so far here, we still try to solve the first problem. Okay, in other words, how the database management system is going to represent the data in files on disk. What we did so far, we start with the files, okay, or file. Then we said the file is going to be broken down into a sequence of blocks or pages, and we can lay out these pages on the disk. Yeah, we show you that we have a different ways in order to organize, or different file organization in order to allow me to keep tracking for these blocks that are stored in the disk. Then after that, we take a look at how can we organize the page itself from the side, how it looks like. Then after that, we took a look at how can we lay out the tuples inside this disk, this page itself. But we didn't say anything about how can we determine or anything about the internal representation, the actual bits that for the value that's going to be stored in the tuples. For example, last time we stopped at the part that we have a tuple, and inside the tuple is going to have a table, and then I have a variable data. Now we need to take a look, how can we store the variable data in binary representation? It's going to be stored in the disk, how it looks like. Then after that, we're going to talk about the system catalog, which, I mean, the way that the database management system can tell whether and relation exists in table or not, in database or not, whether there's an index or not, and etc. Okay, and then after that we're gonna talk take a look at the different storage models, different way to how to store the data. So far that we store the data in tuple based or the row based, we can see that we have a different storage model. We call this one column based. We're gonna see how can we do this one in order to store our data in column based. Then after that, I'm gonna go through a few examples, just show you different ways how can we modify or modification of the tuples. We're gonna update or delete or insert and etc. Okay. So here, the tuple storage here, tuple essentially is the sequence of bytes. And remember last time we said the tuple is going to do what it looks like. You have a tuple is going to have a two parts header, and also going to have the attribute value or data. Yeah, but the data is going to be like bytes, like a sequence of bits. Okay, so it's the job of the database management system in order to help us in order to interpret. I mean, what kind of information is going to be stored there? Yeah. For example, this is the value that corresponds with this attributes. At the same time, the operating system doesn't know anything about the context here. What's going on, the only thing that the operating system understands is this part to say, this is byte of sequence of data, of something. What's this? I don't know. Okay? So the database management system catalog, which contains, I mean, the schema information that is going to help me about all the tables stored in the database, and also tell me, for example, what is the tuple layout. We say the tuple layout because the schema of the catalog database, database system catalog is going to contain the schema. What do you mean by the schema? It's going to be the structure or describing the structure of all the tables that's stored in the database. So by describing the structure, I know that, for example, the attribute A is the data type is, for example, integer, and the attribute B that's stored in this relation that the data type is varchar or whatever. Okay, so what we have right now, or what data that we have this, I mean, the data items or the attributes that we can define. It might be salary, it might be name, it might be date, picture, whatever. So different types of data. And what we have available here to store the data is byte. Okay, that's what we consider as 8 bits. So now the question here, how can a database is going to store these bytes for values? For example, we do have different, I mean, data types, okay, that can be stored in the tuple. It might be integers, it might be variable precision, I mean, numbers, or fixed point precision numbers. I'm going to talk about this one more details. It might be variable length values and dates and times. So in other words, I do have, for example, integer, I do have maybe float number, double, a blob, date times temp, so different data types, char, varchar, etc. We have a different data types, and we need to figure out a way, how can we store them in the disk? So all these data types that we have can be one of the following categories, the integers up to the dates and times. So let's take a look at one at a time from the data representation with more details. So the way, I mean, how the database store the bytes for the value, for example, for the integer, big integer, small integer, tiny integer, we are going to use the C or C++ representations here. What does that mean here? That means the way that for the most of the database management system that's used in order to represent data from the type integer or big integer or small integer or tiny integer, it's going to do the exact thing that or technique representation algorithm or technique used in C or C++. In other words, what they're going to use is they're going to rely on what is called IEEE 754 standards. This one. Okay? So that means if you write your code in C or C++ and you create this data, for example, as say integer or big integer or tiny integer, so the same exact representation for the database is going to rely on the same exact representation that used by the C or C++. So I didn't need to convert to perform any conversions. For the float of the year and against the numeric and the decimal, it's different here. So we're going to see that for the float and the year number, the database management system is going to use or rely on what's the IEEE 754 standard in order to store the data, which we do have a problem in this case because if you have a float and a real data type, we cannot guarantee that the accuracy of the data. Okay. If you use the numeric and decimal, that means you have to use the fixed point decimal. I'm going to show a fixed point decimal that in order to ensure that the accuracy of the data can be reserved. So I'm going to elaborate this one later in more details, okay? And for the varchar or the var binary or text, blob, etc., this looks like here, I'm going to use what is called, the variable length values here. So you can specify like an array, and this array that, for example, if you have a char 5, let's give you a quick example here. If you have a char 5, the simple thing I can do here, I can generate create an array, and the array that contains this information. For example, the first one is going to tell me, for example, how many bytes. I'm going to use 5 bytes, and here I need to store 1, 2, 3, 4, 5. This is the way that I'm going to store the char, for example. The size of the char and the 5, that means I'm going to use 5 bytes in order to store the char. If you have a varchar, you can use different, we call variable size. That means in this case, we have different ways. The simple way that the same thing I did with the char, you have to use, for example, if you said varchar n, that means you have to reserve n plus 1 bytes. Use one first byte in order to decide the size or the number of bytes that are going to be stored here, and the rest of the n bytes in order to store the data. Sometimes you are not going to utilize all the bytes that you reserve. So one way to perform that, maybe you can reserve n plus 1, and the rest that you're not going to use, maybe you have a special character in order to identify that the database management system, this part is not used. So if you try to compress the data, you can eliminate this part. I'm not going to focus in the varchar more details, just I'm interested to show you that what the difference between float and the real number and the numeric and decimal. For the time and date timestamp, it depends, 32, 64 bits integer. It depends on the data type that you work with, a database management system. But most of the database system, they start, store the number of microseconds since the unique epoch. That means the January 1st, 1970. Okay, so let's take a look at the integers more details here. As we said, the integers, that means for the way that most database use here in order to represent the dates, and the integer is gonna rely in the same way that used in the C or C++. So you define this one an integer, it's gonna be the same representation. So since we're writing our code in C or C++, with the case in the Postgres, for example, you're going to see that you just generate an integer, then you are fine. Okay? So you didn't need to have a special handle technique in order to deal with. For the variable precision numbers here, there's a different story here. The variable precision numbers is the one that when you define your variable as a float or year or double. If you do this one, and that's what you are familiar with any programming language, we try to avoid these data types if you try to reserve the accuracy of the data. If you have working with the monetary data or with, say, scientific information data that I prefer to use, for example, big decimal number or whatever, it depends with the Java, for example. Here, we are not going to use the float, real integer, double. We're going to use the different data types. We're going to use the numeric or the decimal. Okay? So again, if you define your data variable precision numbers, so that means gonna be this is the internal the standard that's used by C and C++ with IEEE 745 standards. And this is just for your information. It's like industrial specification of how to represent the numbers internally. So this kind of information, data types, is fast, okay? Because the reason behind this one, I don't need to have a special handling of these data types. I may rely the whatever C or C++, if you use my code in order to define my variable, and done. It's gonna take care for the rest. And so for the float and real double, we don't have a problem, but we do have, for the representation, but we do have a problem with the accuracy. That's what we call rounding errors. I think all of you are familiar with the rounding errors. That means we try to store or represent the data in real numbers, and you didn't have enough space in order to represent the serial number. It looks like we have an overflow. For example, the digit number can be stored within, let's say, for example, 32 bytes. And the data gonna be stored in more than 32 bytes. So what's gonna happen for the numbers gonna be left over? It's gonna be rounded to the nearest one. That's why we have a problem. That's why we have one problem with the rounding issue. So I'll give you an example here. If you write this code in C language, okay, and here what we did here, we tried to compute, the addition for two, float numbers, and the result we expected gonna be 0.3. Then we compare this one with the constant value 0.3, and we inform the system, please give us up to the 20 decimal, digits after the decimal points. Yeah, if you run this code here, we expect the result is gonna be the same. But if you take a look here, what's gonna happen here? That's the different representations that we have. The actual representation slide the system looks like. So if you said x plus y here, the result is going to be 0.3, it's going to be 0.3, so not accurate one. If you said 0.3 as a constant value, try to print this one, you figure out that the result is not accurate, it's not the same. So we do have a problem here. So again, in order to, if you have the data type that I'm going to deal with, or if the user uses the numeric data or use the decimal data, that means this numeric or decimal data type is going to be represented differently. Okay? If the user uses float or real or double, whatever it is, when the user creates a database, the relations, so we don't have a problem. We can just use the float or real number that defined using the IEEE 745 for standards, or specified by that standard. So in this case, what we're going to do here is with the data representation, I'm going to use the fixed point precision numbers. Within this case, the numeric data types with arbitrary precision and scale. That's why if you are familiar with Postgres, for example, when you create the numeric data types, you need to specify two things, mainly. The first one you're going to say is numeric, and they say this is the precision, and also you need to specify the scale. So what's the precision here? This means, I guess, if I recall, yeah, this is the number of digits of both sides of the decimal numbers. So, for example, we have example quick here. If I define, the user define this data, types, for example. I need to finish typing in order to see, okay? If you define something like this, numeric, for example, 10 and 20, comma 2. So the precision is 10 and the scale is 2. So the precision gonna tell us identify the number of digits including both sides. When you say both sides, that means the number of digits that before the decimal point and the after decimal point. That means you're gonna see 10 numbers in total. 2 of them after the decimal point. Okay? So how can we store this information here? So typically, in order to store this information here, I need to modify or create or do more effort in this case. So what I'm gonna do here, I'm gonna store this one in special, data structure or structure, okay? And this one is gonna store this information, numeric value or the decimal value, the similar way that we use the bar chart, kind of. It looks like I'm gonna store the number as a string. Then after that, I need to find a way in order to recover or retrieve the original data. But you have to be, in this case, the performance penalty, because you have to do a lot of work. I'm going to show you the problem in order to get the accuracy. So this is the way that the numeric, the Postgres, if you take a look to the numeric file, I mean .c, yeah, you see that how they use working with the numeric data and more details. You see that they have special handling in this case. If you have a float, we say with decimal, the only thing you need to do just to define this one as a float, done. But if you want to, you define this one as a numerical, etc., that means there's a special handling in this case. So you have a write code. In this code, you have a structure. The structure is gonna have the number of digits and the weight and scale, etc. So some of them is gonna be, it depends. Some of them is gonna be tell you the total number of digits. I mean the both sides. Then after that, the scale is gonna count. I mean the number of decimal digits. I mean in the fraction part. Yeah, and it says the positive and negative, and you see the data is going to be stored at the numeric data, or digit, all the digits is going to be stored as what? As a char. So that means if you have 3.55, it's going to be 355 stored together as one character. So we keep the accuracy 100%, but we need to find a way in order to interpret this data. So if you take a look, if you want to see, for example, more details, you can check, Postgres source code is available, and you check the numeric.c file, and you see that this is the way that it's going to handle just add two numeric data or file, data types. You see that the job is too large. You have to perform large code in order just to add two numbers or two data, attributes from the numeric data types. And if you compare this one, you try to compare, for example, add two attributes from boolean, say from float number, etc. The only thing you say is the first number plus the second number, because you didn't need to do extra job and take care for the internal representation. Compare this one special card in order to make to handle in order to achieve the accuracy, etc. Okay, so. Again, I spoke about this one. I talked about this one before. When you talk about the variable length data here, it looks like here we have an array in order to store the varchar, binary text, blob, add, etc. So it like has a header that keeps track of the length of the string. Remember we showed that the char and the varchar said you have like an array of bytes, and we need the header of the first byte is gonna keep tracking the number of bytes that you used. Yeah, it makes it easier for us in order to jump the next value. We need to make sure that we have a correct structure and easy structure in order to allow me to navigate my way within. Find the exact thing. Why I need to keep, again, in this case, if I have a varchar or binary, etc., I need to keep tracking the number of the size or the number of bytes used in order to jump to the next one. Because remember, what I'm going to store here, store this one, all the information there as a sequence of bytes. I'm not going to have the order. I'm not going to say the first one is going to start from this part of that, then done. No, all of them are going to be as a sequence of bytes, and the header is going to help me in order to decide and navigate my way, in order to jump which data or jump to the next value, and etc. So, what if, that's what it's going to be. So here it's going to be, A is going to be so bytes, whatever, based on the conversion that we have. Then what if we have a situation that one attribute value exceeds the size of the single page? What do I need to do in this case? So in this case, remember, the page is 4 kilobytes. Yeah, for example, Postgres. And you want a database page. And you try to insert, new tuple, and the size of tuple, one value of this attribute is exceed the size of the the database page. So in this case, I need to deal with this one in two different ways. The simple thing, I can store this, the value that caused the problem or larger than the page in what is called the overflow page. So you create another page, and this page, when you create that page, that means you create a new page, and this page is going to have the same structure. It's going to have the same structure for any single page. Yeah? And this page is going to have a header, it's going to have offset array, and etc. And the way that will store the data, the same way that we did in the rest of the page. It's the normal page, but it's going to contain information that, and here in this case, I need to keep tracking or add the address for where can I reach this page. It's going to be the page ID, and might be the offset because you need to find a way how to get access to this one. So when I'm going to use the separate overflow, it depends on the database. The database management system, they do different stuff, okay? For the Postgres, they call this one toast, okay? Which, the oversized attribute storage technique. If you want to learn more, you can click about this one in order to learn more about what this technique looks like. It's like overflow, okay? And this overflow that I'm gonna decide when I'm going to decide, or the database management system or Postgres is gonna decide to store this data in the overflow page or the toss technique if the size is exceed or greater than 2 kilobytes. So whatever the attribute that you try to store, the tuple is greater than 2 kilobytes, that means you have to store this one in the external or in overflow page. For the MySQL, is going to do that, if the overflow is going to use the overflow if the size of the tuple or the attribute is greater than the half size of the page. Okay? For the SQL Server, it's going to be the overflow if the greater than the size of the page. So if equal or less than a little bit the size of the page is fine. If exceed the size of the page, that means you have to store this one in overflow. Someone wonder, say, oh, the same problem here. So if they exceed the size of the page, how can you deal with this one? Now you're gonna deal with different story. You can use the fragmentation. You have to divide this one into compress the data and etc. Whereas that's out of scope is this part. That's the only thing you need to think about here. That means if the size of the data or the tuple or the say attributes is greater than the size of the page, or it depends on the criteria, different databases do different stuff. That means you have to store this data, or this tuple is going to be stored, let's say, on the overflow page. The other thing that we can use alternative approach, we can use external value storage, which is a different story here. So that system, some system allow you to store that I'm not going to use the page inside the database. No, I'm going to use external files. So that means, for example, assume that the C is the movie, okay? Mission Impossible, whatever. Yeah, and this one maybe 2 giga or 3 giga, whatever, gigabytes. If I store this one in the giga, keeping that, it's going to consume the space in my database, and also it's going to require for me to have too many disk input output operation in order to retrieve the whole data. I have a solution. What I'm going to do here, I'm going to specify path on specific data and my file, and to store this file there. And the key just have the path of the where I can find the file or the rest of the data in the external file. Yeah, okay? So it's treated as like a blob page. And the Oracle called this one binary file, I think, B file, data types, which is going to deal differently. For the Microsoft, it's going to have this data type, is going to be use the file stream, okay? And the problem with this one, the database management system cannot manipulate the content of the external files. In order to access one, that means you have to use whatever this file written, what software or application written by, in order to manipulate this one. But we have two different major things here. The one that use the variable length. The large value, I'm going to use overflow storage base. If I do this one, that means I'm still being able to use whatever the database management system is going to offer. Remember that if the system tries to modify the data in the overflow and the overflow is a crash or something, disk failure, etc., I can't use the log recovery that provided by the database management system in order to restore the original or the consistent state. But in this case here, no, it's outside of control of database management system. But the good thing here, since as I mentioned that I'm going to store maybe data is like movie, pictures, that has a large amount of space, so it's better to store this information in the external, storage or external file. We do have something here I need to add here. For example, if you have an overflow page here, that means I need to, if you have use an overflow page, if the size of the attribute is greater than the size of the page, I can use compression technique in order to compress the data. And most of the things that the data is going to be used, the overflow page, or going to be larger than the size of the page, mainly it's going to be static data. So in this case, it's okay to compress them, because once you need access to the data, I can uncompress them, and it looks like I'm not going to modify the data more frequently.
Professor?
Yeah.
Question here.
Yeah.
So in this size of bundle page is 4 KB, right?
Yeah.
So then why Postgres, like it is mentioned for Postgres, the size is like greater than 2 KB, and then for MySQL greater than half of the size of the page. Then
so each one, as I mentioned, each database system is going to do its own way to implement that.
But that is not larger than the size of the page, right?
No. For this one is this one because this one for the Postgres they have a different way to deal with this one. They use the toss. Toss is gonna use the overflow if the file or the attributes is greater than 2 kilobytes. You have to do the toss. You have to use overflow. That's the Postgres. This is, I just tell you, the idea, the situation, that if the attribute you try to store is like greater than the size of the page, we need to act. But remember, different database systems do different stuff. Each of them it has its own idea, own way in order to implement that. So that's why for the Postgres, they say if they're greater than 2 kilobytes, we have to use overflow. For the MySQL, if it's greater than half of the size, you have to do overflow.
Okay.
Clear? Good. So there's one paper, if you're interested, I know it's old paper, but still said whether you use blob or not, whether you're going to use, for example, external storage or not. So if you have a file or not, if you have time, you can check this one. It's interesting, if you have a chance to, or interesting to read more. Now, take a look at the dates and times. We covered this one, but it doesn't hurt to repeat this one again. Usually it's going to be represented as the numbers of micro or millisecond. This is the most database management system. But remember, that might be the minor variations. Or it looks like this is the standard, but everyone is going to have its own way in order to implement the stuff, to be different. So most of them are going to use, count the time, the number of milliseconds or seconds or microseconds since, the unique epoch is going to be, January 1st, 1970. Okay? And as example, time, date, and timestamp. Of course, each of them is going to have different size. Each of them is going to have 32 bytes, for example, 64, and etc. That's what we're going to, when you represent, the attribute in the tuple. Okay?
I have one more question. So out of the two, in case of overflow or the external value, which one is preferred? Or it depends on the...
An implementation, I can tell. So that's why you see, that's why you need to read more about the actual, what the Postgres is doing in this situation.
Okay.
Yeah,
okay.
mainly going to use overflow here. Yeah. But as I mentioned, some of them, it's better. For sometimes you have external file that, what if the size of the data, for example, as the movie, is 3 giga or 100 gigabytes. Mm-hmm. So for the user, it's better to do what? Do your external file.
Okay.
That's better, yeah. And especially, it's like static data. You're not going to modify the data. For example, when you fetch or perform a query and etc., generally speaking, you are not going to retrieve this one every time you access the data.
Mm-hmm. Okay.
So the system catalog, we talked about this one before, is like the database management system must store metadata. We need to know, for example, a way that to know the structure of the database that we store the disk. Yeah, the tables, the relations, for example, the attributes, the structure of the attributes. Because I know the structure of the attribute, I know the size, I know how can we retrieve the data. Okay, so we need to find, for example, information about the tables, about the columns, for example, index, views, users, permissions, internal statistic information. These, for example, the number of unique value for specific attributes. We're gonna use this one later when you talk about the query optimization in order to figure out the best way in order to find the best plan in order to execute the query. So we need to get back to the internal statistic information in order to try to help us in order to estimate the size of the cost, estimate the cost for you in order to execute the query and etc. So anyway, we need to have a metadata about the data, yeah, which is going to be stored in the internal catalog. Okay, so the metadata, as I mentioned, contains information about the tables and index, views, and etc. Almost every database management system stores these data in the catalogs in itself. So this means it's going to be stored this one inside the database system. Yeah. And now we have like a dilemma here, because every time you try, for example, to access the data or the access file, you need to consult the schema. Yeah, and now the schema or the database metadata or the schema of the catalog is going to be stored inside the database. So that means it's going to be stored in file inside the database. So it looks like in order to access the internal schema, or let's say the system catalogs, you need to consult the system catalog in order to find the name of the relation, in order to access the relation, and also in order to figure out the structure or how the data is going to be stored inside those relations. Because remember, it's going to be file, and file can be, break it down into a bunch of blocks, and these blocks is going to be stored in the disk. But what they're doing here, it looks like object abstraction around the tuples. It looks like we have a special in our when you build the database management system, they have like exception way in order, or a unique way in order to deal with the system catalogs. So in this case, it looks like we have a special specialized code in order to take care, access the catalogs data or tables with different way. So it's not gonna access the way similar the way that we access the normal relations. So how can we access the system catalogs? I guess most of you or all of you are familiar because you're working with the database for a long time. So you know that, for example, how can we query or how can we access this information schema? Although it's internal data used by only the database system inside, because in order to figure out what kind of navigate their way and figure out what relations stored, how can we extract or interrupt, the relations that are going to be stored in this sequence of bytes in the disk. But and the standard or SQL standard allow us in order to, for example, to provide us with some SQL query, allow us in order to retrieve or access these informations. Plus, most of the database management system, they have like non-standard shortcut. So that means instead you use, the standard for, way in order to query, let's say, the information schema, is allow you to use the shortcut in order to access or retrieve this information. So the first one here, this is, in order to list all the tables that are in the current database, that's what we're gonna cover. This is SQL 92 standard. You're gonna say select a star from the information schema dot tables where the table catalog equal the database name that you're looking for. Other we need whatever. If you put the database, it's gonna give you the database itself. Anyway, so in this case, that's the standard set. You can do something like this, but if you are familiar with the Postgres, you can do /d. If you are familiar with MySQL, you can use show tables only. So it looks like shortcut is gonna internally implement this SQL 92 statement in order to allow us in order to list all the tables in the current database, etc. As I mentioned next lecture, I'm gonna try to maybe spend the first 20 to 30 minutes to give you like some practice. We try to do like some experiments to see using the Postgres to store the data, how can we retrieve the schema, and to try to put all the data, the tutorial that we're gonna do next week in 1 or 2 files, so you allow you to share it with you so you can test this when you are on your time. So in order to access the table schema, we can access them similar. This is the standard for the SQL 92. This is the way how to access the columns for the specific table, and this is for the Postgres. You have the /d and the name of the relation that display the columns for the specific table. For the MySQL, it's gonna just describe a student, and SQLite is gonna dot schema student. So each database management system does things differently. They have we have something standard, but each of them has its own way. Each of them is gonna try to be come up with something to be special. So we're done for the data representations. So far, I guess we're ready to finish the coding assignment 1. Thanks, guys. That's all for today. See you next week.